My name is Dustin Ho with Applied Material. Thanks for Professor Guo and next forum invitation. Here I'd like to present compound semiconductor technology for next generation automotive and 5G communication. First, we can look at our semiconductor device landscape and some history. Semiconductors start from the 1970, and in the beginning will be the mainframe computer is dominant, but only about 100,000 units. Then the PC, internet, and so we drive up the unit to 100 millions of the units. And I think right now everybody even have more than one desktop or a laptop computer. And also during this time, we have the more secret because the Moore's law driven and every 18 months to 2 years, and then we need to refresh our computer. Then thanks to the mobile phone, smartphone, then and the social media, and now we have the billions of the units for, and everybody maybe have more than 2 phones, one for the work, one for the personal. So the secret become less. Now we are very exciting time to see the AI big data area, and I think everybody just heard about a few days ago about the Tesla AI Day. So this was driving all the automobile, autonomous driving, and also other industry. So therefore, about 3 years ago, we applied forming a new group called Icaps. So I mean IoT, C mean communication, A for automobile, P for power, and S for the sensor. For the IoT, because all the AI and the big data need to connect everything. So the smartphone and industry 4.0, smart transportation and building automation, control and security. Communication, everybody have a smartphone, and right now we go to the 5G infrastructure, and even right now just the less than 6 gigahertz, future will be milliwave, and so it increase the data and video demand, and then we have also the silicon photonic for data transmission. For the automobile side, autonomous vehicle and the EV car is the big driving force right now, and it will be the key topic for today. And everything we need a power. So power is very important for the data center, renewable energy, and consumer and appliance. And right now we also want the global warming effect, reduce the carbon emission. So need a more efficient. That's why we have the compound semi, silicon carbide, gallium nitride. And all the sensor, the wearable technology, touch, and we had a facial recognition and gesture recognition. So there's a lot of big application for the future. Now look at it from the device, on the wafer inflection. Applied Material is selling the wafer fabrication equipment. So we really like to see what's going on the wafer inflection. For the power and RF technology, so because for the EV car, so it migrate to the compound semi and the wafer material already from the 4-inch to 6-inch. And silicon carbide wafer processing is for the high voltage MOSFET. And gallium is for the fast charging. So right now gallium have the epitaxy on the gallium nitride or silicon carbide or silicon. And the advanced PVD for magnetic material deposition, and for silicon power, IGBT and super junctions, and there's few companies already migrate to 300 millimeter. And then for the RF filter, we have the aluminum nitride, and then we have scandium doped aluminum nitride film for the next generation device. For the CMOS image sensor, CIS, right? Everybody have a cell phone with a lot of camera, and you want more pixel. So they have a lot of improvement on the CIS side. So we have a normal organic filter material for high efficiency photodiode, and the DDI advanced CVD trench field, and ultra high voltage implanter for the deep pixel technology. Also we had a advanced process doping for the high aspect ratio pixel, and also advanced packaging for the TSV and integrate with the memory and more. For the optical side, now for the autonomous driving cars or the LiDAR will be the future, and the miniature and the bin scale for the LiDAR will be key inflection, and also because in the laser diode integrate with the CMOS, and also for the AR/VR we had a photonic waveguide, and also Applied Material joined the LASA alliance in working on the waveguide, and I had a single mode fiber active alignment, and the micro LED they say will be the future display. So their mass transfer and assembly need to improve to drive the cost down. And because you shrink the size of the micro LED, so quantum efficiency, EQE, they also need to improve. MEMS we use a lot for the speaker and the microphone, and right in the future, and the gyroscope. And need to more or less integrate with the CMOS, and we need a new low-temp conformal film and high aspiration structure, and a new acoustic piezo like PCT, and also the lead-free material for piezo occlusion. And this also bring out a new substrate, now from silicon to compound semi, such as gallium arsenide, silicon carbide, and gallium nitride. So the process technology for silicon carbide wafering is very important in the high temperature implanter and epi for silicon carbide device, and the transition to the 6-inch and 8-inch, and just like the silicon 30 years ago was transition from the batch to single wafer processing. And then also the ALD and ALE for the GaN will be very important, and MOSFET for the 3-5 material growth, so it can reduce the cost for the epitaxy and more. Applied Material offer a lot of equipment for our industry. To simplify, you can see you have a clean, deposition, remove or etch, and modify and analyze. The dry cleaning for deposition, you have metallization PVD or the metal CVD, and epitaxy, plating, direct for CVD, ALD. For the remove, you have the CMP polishing, you can etch, or you have a wet clean. For modify, you have ion implanter, and then the RTP for oxidation, nitridation, and annealing. For the metrology, we have the CD-SEM, E-beam metrology, etc. So inside Applied Material, we have our expertise, so we can combine all this experience to contribute to serve our industry. Now we look at the Tesla as an example. So Tesla is kind of the leader, the selling leader for the EV cell, and they are the first one to adapt silicon carbide technology to the power switch. So traditionally, the IGBT is they use the 48 silicon carbide MOSFET device. And look at the usage for the silicon carbide, right? And here's the projection. So like last year and this year will be like they need 91,000 of the wafer for silicon carbide 6-inch wafer equivalent. So that means it's about 8K wafer start per month. And by 2024 projection, they need 186,000 wafer and 16K wafer start per month. And this only have one car model already drive out so many 6-inch wafer. And look at all the automotive industry come to silicon carbide, so the demand is humongous. And now we look at the MOSFET process. This is a typical process for the trench gate. You have the silicon carbide substrate, and then you need to do the epitaxy, then you need to do the etch. And I'm sorry, this the cartoon not really good because to reduce the high voltage breakdown, so the bottom of the etch is more round, it's not rectangle. Okay. Then you have the trench gate, and then you need the implant because it's N-type substrate, you need a P doping and a P plus doping because silicon carbide is very hot material, so you need a high temperature for the doping, and then you can annealing at a high temperature, more than 1700 C, and then you have the thermal oxidation to the gate oxide, and then you have the gate electrode LPCVD for the conformal film, then you have the CVD for the ILD, and then PVD for the metallization, and then cross contact, and the spin coating for the top polyimide. And on the backside, you need the sealing, and we also have the backside metallization, and we have a new accelerator PVD from batch type, so you can, because the backside not so critical, and you can reduce the cost. For silicon carbide key inflection, right now I already have the Schottky barrier diode integrate with the MOSFET. In the future, then we'll go to the trench gate. Right now, only the ROM and Infineon can make the production of the trench gate, and rest of the industry is coming up. So in the future, everybody will go to the trench gate. And then right now, you see the wafer to start from 350 micron to 150 micron thickness to the heat dissipation. In the future, then you will even thinner to like 100 micron, even 50 micron. And then maybe the starting wafer thickness even can reduce from 350 to 150. You don't need to be that thick. And then for the future high voltage, and then you will go to the super junction. And the super junction for the ultra high voltage, there will be, and then you can help to reduce the epitaxy thickness. So there's a lot of inflection, of course, waiting, and also for the wafer size, already 6-inch in production, and then the future next 2 years will transition to 8-inch silicon carbide wafer. So the tool used for the silicon carbide process, like CMP for the tungsten, for planarization, and epitaxy is needed the high temperature. We don't offer this one for now. And the imprint, because silicon carbide in the high temperature imprinter, and annealing, you need more than 1700 C high temperature annealing. And the edge is very critical for the trench edge, and you have a thermal oxidation, and then you have the ALD or LPCVD for the conformal film isolation, and PCVD passivation. In the PVD for metallization, and the backside also kind of plating, and the metrology to inspection and defect is very important too. So probably offer most the equipment, process equipment tool for this industry also. Now look at the gallium nitride for the power. For the gallium nitride, because of faster charge, and right now you can divide either low voltage and high voltage. Typically it's 100 volt. Maybe some customer is 120 or 200 volt. And then most right now for high voltage is 650 volt. And right now already company will offer 800 volt also. So for the low voltage, low power is for the wireless charging, right? And then for the 650 high voltage, right, faster charging. For the, especially the Apple discontinue to provide the charge adapter, so this the faster charge for the traveler very important, is driving this market up. And in future gaming desktop and the power server, data center server power, and then future even for the EV car onboard charger too. So here look at the market forecast for the GaN power. The most big one is on the faster charge. It is driving up this market. And next will be automobile, EV car. Then will be the data center, the 5G communication. And then the two inflection important one will be the development of toward integration, because you need to combine the GaN HEMT HEMT with the integration of the IC to better control for the faster switching. And also most right now GaN on silicon production is in 6-inch, but you can see more and more company will transition to 8-inch GaN on silicon. So our equipment is the fully compatible, is for 6-inch and 8-inch. You just need to change the process kit, you can do the both. Here is the typical GaN on silicon, normally off-hand over process flow. From the substrate can be silicon or silicon carbide, then the MOCVD, you need ammonium nitride seed layer and the buffer layer, and then the GaN SiC GaN layer. And then you need alkane for the 2DG, and then you have another GaN. Then you need to do the edge. Then your CVD for GaN metal photoresist, and then you have the ALE to remove, and then remove the GaN, but you need not protect the alkane area. So this is very critical for the high selectivity. Then in the ALD or LPCVD for the nitride, silicon nitride insulation to protect the alkane area. Then you need another edge for the open contact for the source and drain. Then PVD metallization, and then PECVD for ILD. Then another edge PVD for the metallization. And then you also sometimes for the backside you can have the backside part. So we offer most the process tool for this process. Now look at again key inflection and opportunity. Because the GaN device need to like shrinkage, so it can cause a reduction, and this will drive up the current intensity. And also the GaN structure right have different approach, like P-GaN or so the recess or so the MIS-HAM or different process. And then because they are switching so fast to balance out, so in the future you need like one of these, you have a high and low side to balance out. And more important, you need to have a control IC combined with the GaN power. And far long away, they will go to the vertical GaN, because the GaN substrate right now is still small size and small quantity and only 4-inch available. But in future, if they can have a 6-inch available, and then will be vertical GaN, it's actually will be very good for the high voltage, and the performance even could be better or even equal or better than silicon carbide. So we will wait to see. We will be very interested in the future development on the GaN device side. And here is the process equipment for the GaN process. So you have the CMP and the MOCVD for the epitaxy, and you have the implanter for the isolation and the gate doping, and the annealing in the gate edge, especially the high selectivity ALE for the GaN alkane, and then some oxidation furnace, and then you have this ALD or LPCVD for the isolation, then PECVD passivation, PVD metallization, the plating, and again in the metrology for inspection defect review. Now for the RF side, the RF GaN. Now we see on the 2019, right? Most your communication can be silicon almost, and then gallium arsenide may be dominant for the cell phone. In the future, for the 5G, right now we offer less than 6 gigahertz, so you start to transition to GaN nitride. When you go to a higher frequency, a mid wave, the small cell, then GaN will be in the future. The GaN will make it more market share. It will be very more critical for the 5G communication. And right now, for the cost reason, most of the process will be GaN on silicon for a low voltage, because the mismatch of the GaN on silicon, so the buffer layer is very critical, and the doping uniformity and the stress is very important. So that's why even they have a GST, different kind of substrate engineering available. And then because for the RF application, and this is the RF parasitic leak will be very critical. So the epi defect and the interface for silicon aluminum nitride, it was very important. And omni contact is everybody want to reduce the contact resistance to improve the efficiency, and also need the non-gold omni contact process. And in theory, maybe copper is very good for this one also. Because it's for the RF, so that's why the surface roughness will be critical for the RF application. And this will emphasize the edge and the ALE importance. And with the thermal conductivity, so GaN on silicon only good for the low power because the heat dissipation issue, right? And therefore, right now the industry, you have a two stream. It will be GaN on silicon or GaN on silicon carbide. Silicon carbide will be good for the heat dissipation, but the cost is high. So right now, most GaN on silicon carbide for IF is on the 4-inch because the semi-insulated SiC is very expensive. Maybe future is cost driving down, then maybe everybody can just do the GaN on silicon carbide. But for now, it's the low power will be GaN on silicon and high power will be GaN on silicon carbide. We see. And for the metal, like I say, right now most people will use the gold, but for the theory, for high frequency, the copper will be good candidate to replace the gold. Of course, once you use the copper, we are familiar in the silicon side, but for the GaN, it's brand new GaN, so you need a lot of work and R&D to improve this one. And also the surface passivation, I say the GaN passivation, the surface, reduce the roughness will be very important. So still a lot of improvement needed for us to resolve it. And the typical process for the GaN process flow, very similar to GaN power, is the GaN ham. The main difference will be the T-gate. So start with the MOSFET with the buffer layer into the edge, and then you need and then you have the passivation. You need another edge, so you can form the T-gate, and then you another passivation, ALD and LPCVD passivation isolation. Then the edge for the source and drain contact. Then metallization. Then you have the CVD, PCVD for the ILD, then the PVD for the field plate and source drain pad, then the PCVD ILD, then you need grinding, CMP substrate, and then you have the the nitride hard mask, and then because for the IF, you have the backside TSV edge, and the backside metallization, the gold gap field. And here is some applied material capability to do this one. We do have the PVD for the aluminum nitride buffer layer. For gate metallization, a lot of people concerned about charge damage, so maybe use the e-beam evaporator. But actually, we have long stroke PVD, and it can reduce the charge damage. Then the edge will be very critical for the selectivity of GaN and LGaN, and we have LPCVD for the nitride passivation, and then PVD for the T-gate metal, then ALD, LPCVD isolation passivation, and then standard edge, and the metal PCVD for ILD, then our PVD for the source drain field plate, again another ILD, and we have the CMP for the grinding. Then you have the TSB, we have the TSB for the backside edge, and we also have the plating tool for the gap field. We sell the individual equipment for the individual process film or the depth of the edge, and the integration will be very important. For prime material with the Madden Technology Center in Santa Clara. Also, we joined the New York State Meta Center for the Material Engineering for Technology. You also have the Advanced Packaging Center in Singapore. And we have the applied tool, and then we can access to the diesel and the wet and other inspection tool. And 24/7 operation, we can do the test for our customer. We also have the mask tool, so we can customize the special feature requirement for the mask, the design, and do the modeling, emerging EUV capability. So we can do some testing for the customized test vehicle, not only for the memory transistor pattern, and with CIS and IoT. And we have more than 200 short loop integration development and the test vehicle available. So when the short loop testing flow, the development solving the customer high value problem enable the new material structure in the device. Summary. So for silicon carbide is growing significantly because of the EV traction and the high efficiency. Right now, already go to the 6-inch wafer production. I think 2 years, we will transition to the 8-inch also. And the new process, new material engineering is required to optimize silicon carbide fabrication in high volume manufacturing. For the power GaN, the faster charge is accelerate the growth of the GaN into a more critical market, enterprise and the EV. Right now, the GaN on silicon is on the 6-inch. However, it's transitioning to the 8-inch today now. For RF GaN, it's getting entry for high power and high frequency application. It's driven by the 5G and the millimeter wave telecom application. So reduce the parasitic, improve thermal dissipation, and the CMOS integration is the key trend for the RF GaN. And the substrate for silicon carbide mainly is 4-inch, and it's 6-inch for silicon. But in future will be even the RF GaN will be 6-inch silicon carbide and 8-inch GaN on silicon. Finally, that is our innovation to make it possible. So we continue to invest and on the more and more semiconductor devices will transform the market industry. And we leverage a broad suite of the technology in high volume production for the 6-inch, 8-inch, even 12-inch tool. And applied materials well positioned to support customers in a rapid growth more and more space. And we develop a new equipment capability in material and process for more and more semiconductor application across the different development sites. A new material and process technology through deeper partnership and collaboration with the international partner R&D facility. Thank you for your attention.